Okay, so before you watch this video, you should have already watched Conservation Part 1 and the video on the roller coaster with the man riding the roller coaster and telling you his impressions of it, and the grown man who says "wee" at one point. But anyway, let's use that as our background as we discuss this. That there's this term mechanical energy. Mechanical energy refers to the sum total of all the energies involved in the machine, in this case the roller coaster. And this mechanical energy, we're just going to give it an E with no qualifier on it, is the sum of the kinetic energy and the potential energy of the system during any point. And we're going to assume, again, an isolated system, as we'll talk again here in just a minute. And the amount of work that's done on the system to get it started is what's going to determine the amount of mechanical energy. So for a roller coaster, like the one that you saw in that video, the work done is done by a motor on the first hill, where it's drawn up the hill by a chain or a belt, anyway, somehow driven to the top of the first hill, which increases its potential energy. It does increase its kinetic energy, some as well. But mostly what we're trying to do is build up potential energy. So when you're at the top of that first hill, you have the maximum amount of potential energy. And then as that train crosses the top of the first hill and goes down the other side, that potential energy is converted into kinetic energy. But the total amount of energy is going to basically stay the same. We're going to assume an isolated system that's ideal, and excuse me, no energy gets lost as a result of friction or any of those things. Okay, so the criteria under which momentum was conserved was, again, that we have an isolated system. That means that there are no forces coming from outside the system into the system, and there are no forces leaving the system either. So whatever momentum is in there, it stays in there, and the same thing will be true of energy. So if the mechanical energy is conserved, then it must be true, and that's, again, nothing's coming from the outside or getting out from the inside. Then the change in the kinetic energy and the change in the potential energy added together have to be zero, because we are conserving energy. None is lost, none is gained. Or rearranging that the change in the kinetic energy is the opposite of the change in the potential energy. So if the kinetic energy goes up, the potential energy has to go down, and vice versa. This is very powerful to know that if we have an isolated system, that whatever energy is in the system is going to be there as either kinetic or potential, or a combination of the two of those. And if we want to rewrite that, then we could have this, that the final minus the initial kinetic energy is equal to the final minus the initial. The potential energy is just the opposite of that. Or if you can do it this way, if you want, which just says that the amount of energy you start with equals the amount of energy you end with. And that should look a lot like when we did momentum problems back in the momentum chapter. The momentum to start with equals the momentum we end with. The same thing is true of the energy. The sum total of kinetic and potential energy, which is called the mechanical energy before, equals the mechanical energy afterward. Okay, in the next video, we're going to talk about these roller coasters and apply that mechanical energy and the conservation of energy to those.